Welcome to Body Unified Flow. This is where we simplify complexity and amplify performance. Today, we're diving deep into a really powerful tool for understanding any operation, work sampling. We're going to go way beyond just the definition and get into the nuts and bolts of how you design a study that actually has real statistical power. By the end of this, you'll get the core principles and have the exact tools you need for a valid study. Let's get right into it. So, what is work sampling at its heart? Well, think about it like this. Imagine you want to know how a big election is going to turn out. You don't ask every single voter, right? Of course not. Instead, you pull a carefully chosen representative sample. Work sampling is exactly the same idea, just for business operations. It's built on this powerful idea that a random sample from a large group will pretty much show the same patterns as the whole group. By taking these little random snapshots, we can build an incredibly accurate picture of the entire system without the crazy effort of watching everything all the time. So here's our game plan for today. First, we'll get our heads around the big idea of sampling the whole. Then we'll build the foundation of trust. What makes a study's results actually believable. After that, we'll dig into the absolute must-haves, the mandate of randomness, and the math behind calculating sample size. And we'll wrap it all up by making sure our study gives us true representation. Let's begin. All right, first up, sampling the whole. This is where we make a really important mental shift, moving away from the old school stopwatch method and toward a much smarter statistical view of how work gets done. Now, this is a real game changer. On the left, you've got your traditional time study. It's all about duration. It's asking, how long does it take to do task X? But work sampling, on the right, asks a completely different and frankly more powerful question. What proportion of our time is spent on task X compared to task Y or just waiting around? This shift from duration to proportion is what lets us see the entire forest, not just one tree. It helps us spot those big, system-wide bottlenecks that are holding everything back. And that brings us to a super important point, the foundation of trust. I mean, if your study comes back and says 20% of your team's time is wasted on some issue, you better be able to stand behind that number. The principles we're about to cover are what give your findings that rock-solid credibility. Let's just pause on this for a second. A study's results are only as good as its design. This is everything. You could have the fanciest software in the world, but if your study was designed poorly from the start, well, garbage in, garbage out. So everything we talk about from this point on is about making that foundation completely unshakable. So a defensible study really stands on two absolutely non-negotiable pillars. First, true randomness. This is our shield against bias. It makes sure every single moment has an equal chance of being seen. And second, statistical significance. This is our guarantee that we've collected enough data that our sample is big enough to actually mean something. Get these two right and you're golden. So let's dig into that first pillar a little more, the mandate of randomness. It sounds simple, right? But getting this wrong is one of the easiest ways to ruin your whole study. Because as we're about to see, predictability is the absolute enemy of accuracy. And this leads to a question I hear all the time, and it's a good one. Look, why all the fuss? Why can't we just check in every hour on the hour? It's easy, it's systematic. It seems to make sense, but it's actually a huge trap. So why is that? And this slide tells you exactly why. The moment things become predictable, people change what they're doing. They know you're coming at 2 o'clock, so they make sure they look busy at 2 o'clock. That's called the observer effect, and it completely poisons your data. But with true randomness, you get a real snapshot of a typical moment, because nobody, not even you, knows when the next observation's going to happen. Okay, so we've nailed randomness. Now for that second pillar, statistical significance. This brings us to the most technical part of our talk, but honestly, it's the most important. Calculating the sample size. This is where we stop guessing and start using math to get a real, certain answer. This really is the million-dollar question, isn't it? How many snapshots do we actually need to take to feel confident about our results? Is it 10, 100, 1,000? Well, the good news is we don't have to guess. Statistics gives us a way to figure out the exact number. And there it is. This formula tells us precisely how many observations, or N, that we need. Now, I know, formulas can look a little scary, but don't worry. We're going to walk through every single piece of this, Z, P, and E, so it all makes perfect sense. It's way easier than it looks, I promise. Let's start with P. P is just the estimated proportion of time you think is being spent on whatever you're measuring. It's your starting guess. So say you want to know how much time your team is idle. You need a starting point. A lot of times, you'll just do a tiny pilot study, a few dozen observations, to get a rough idea. If you think people are idle about 20% of the time, then your P is simply 0.20. Next up, Z, the Z-score. This sounds complicated, but all it represents is how confident you want to be in your final answer. Think of it as a guarantee for your data. The industry standard is usually a 95% confidence level. That just means if you ran the study 100 times, your results would be accurate 95 of those times. And for 95% confidence, the Z-score you use is always 1.96. And finally, we have E, which is your margin of error. This just decides how precise your final answer needs to be. So if your result is 20%, is it okay if the real answer is anywhere between 15% and 25%? That would be a margin of error of plus or minus 5%. If you need to be more precise, you need more observations. But for most studies, plus or minus 5% is perfectly fine. So we write E as 0.05.
Okay, let's put it all together and see it in action. Let's say we want to find out how much time call center agents are idle. Step 1, we estimate P. Our pilot study suggests it's about 20%, so P is 0.20. Step 2, we choose Z. We want the standard 95% confidence, so Z is 1.96. Step 3, we set E. We're okay with a precision of plus or minus 5%, so E is 0.05. Now we just plug those numbers into the formula. You run the calculation and you get 245.76, and since we can't do a fraction of an observation, we always round up. So we need 246 observations. See, it's just simple math once you know what the letters mean.
So we have our pillars, randomness, and our magic number of 246 observations. But we're not quite at the finish line. There is one final, absolutely critical piece of the puzzle, which brings us to our last section, ensuring true representation. Because how and when you collect those samples is just as important as how many you collect. To get a real picture, your sampling has to reflect your reality. Is a Monday morning different from a Friday afternoon? You bet it is. What about the night shift versus the day shift? Totally different. So those 246 observations have to be spread out across all shifts, all days of the week. If your business has busy seasons, you need to factor that in too. And if you have separate groups, like different departments, you might use a method called stratified sampling just to make sure each group gets its fair share of observations. If you fail to do this, if you only sample the easy times, you fall into a huge statistical trap called undercoverage bias. It's a fancy name for a simple problem. You've completely ignored a part of your population. If you only sample the day shift, your results tell you absolutely nothing about what happens at night. By spreading your observations out, you avoid this massive flaw. Okay, let's bring it all home. What are the key takeaways for a valid work sampling study? First, remember your goal. You're focused on the proportion of activities. Second, your study must be built on those two pillars, randomness and sample size. Third, don't guess. Use the formula to know exactly how many observations you need. And finally, make absolutely sure your plan represents the entire workflow, all shifts, all days, everything. I want to leave you with this really powerful thought from the source material. By following these steps, by embracing randomness and calculation, you're doing more than just measuring. You are applying rigor. And it's that rigor that turns a simple guess into a verifiable, defensible engineering discipline. These techniques we've talked about today are like a special lens, one that can reveal all the hidden problems and opportunities hiding in any process. They give you the power to see what's really going on. So the only question left is this: what hidden truths about your workflow are you ready to uncover? Thank you so much for joining us for this deep dive into planning a work sampling study. The research papers that helped inform this explainer are up on the screen for you. We hope this has given you the tools and the confidence to better understand your own operations. Thanks for watching.